So this video is on collision theory. Collision theory basically says that molecules need to collide with each other. So I'm not going to write that down. And they have to collide to do two things. Basically, one, they have to be able to break the old bonds, okay, prior to forming new ones. That's kind of one thing. Oops. All right. And when they do this collision, they have to collide in a certain way. So they have to collide with enough energy, and that energy is going to be called activation energy, right? And that could be either forward or reverse, which you'll see in the potential energy diagrams, and with the proper orientation. Okay, that just means they have to knock into each other in the proper way. I mean, you can think of this about like enzymes and substrates, like what you learned in the living environment. So you have an enzyme like this, and your teacher draws it like this. You know, if the molecule bangs into the enzyme this way, well, it's not going to get into the active site. It has to bang into it this way so they can, you know, because they're not thinking. They're just molecules, and when they bang into it with the right orientation in three-dimensional space, then they can form the enzyme substrate complex or whatever else the molecules are doing before they form the product. So for a collision to be effective, it has to have the right amount of energy, what's called the activation energy, and it has to have the proper orientation. Okay, and because of this, we can figure out ways to change the rate of a reaction. The rate of a reaction is like any rate. Rate could be miles per hour, or how many gallons of water flow down a river per unit of time. In this particular case, it's a change. It's always a change in concentration, which I'm going to use brackets for, but this is really in molarity, over delta T. And this is basically like, you know, change in Y over change in X. You know, it's like slope, essentially. So you can watch a reaction. What usually happens is if you start off with, you know, reactant over here and you start with product over here, the reactant will start to go down like this and the product will start to go up like this. And if it's a closed container, by the way, it will reach equilibrium, and you'll recognize equilibrium because when it gets to equilibrium, these lines will just flatten off like this at some point. Okay, but initially we can look at the slope of this line here or the slope of this line here, and that's how fast the reaction is going. All right, now catalysts and other things can affect the rate. So things like temperature, and there's all sorts of variables that can affect temperature. They won't affect the equilibrium situation unless you change temperature. All they'll do is they'll get to equilibrium faster if you increase the rate. So let's talk about things that can speed up or slow down the rate of a chemical reaction. Okay, variables that can affect this. Number one is temperature. And obviously if you increase the temperature, all right, you have both faster collisions and they have more energy. So they give you a question on the regions. They might wrench on things, but if you have to pick 10 Kelvin versus, you know, 20 Kelvin, that's going to be faster. Make sure that means less time. Faster people take less time to get places. Okay. Second variable is concentration. All right. If you increase the molarity of something, which is increasing the concentration, that means you know, if originally it was 1 molar, there's a few particles like this, right? If you change it from 1 molar to, let's say, 2 molar, so now it's there's more particles in a given amount of space, and they're going to hit each other more often, more collisions. All right. Important variable here that's kind of a sub-variable. This is when you're dealing with gases, okay, you can talk about sort of like pressure, but only pressure when you're changing the volume of the container. So if, let's say you have a container like this, okay, with X number of molecules in here, you know, if you make the container, you know, this big now, you have the same number of molecules in a smaller amount of space. And because of that, it's almost like you've changed the molarity. You have more moles in that particular number of volume. So that means the chance of the particles banging into each other is greater. All right. I mean, you can picture this like this. If there's 10 molecules here, you know, and there's 10 molecules in a smaller space, they're going to hit each other more often. Okay, variable number 3, I think I'm doing numbers, not letters, would be surface area. Not going to get into this too much. More surface area means faster. Keep it really simple here. Just make sure you're clear, like if they give you like, you know, boulders, you know, versus pebbles, you know, versus, you know, dust, this is going to be faster, okay? So what we got? We got temperature so far, concentration and pressure, which pressure only affects gases as usual. We have surface area. What else? Let's see what we got here. Catalyst. Okay, they want you to know this lowers the activation energy. Okay, it changes the mechanism. Essentially what it does is, if let's say a collision had to have a certain amount of energy for it to be effective, now a collision with less energy is now effective. Which means the more the collisions you gotta think of it, sometimes molecules are going to bounce off each other, and sometimes they're going to form the activated complex. Without the catalyst, some of the collisions which they bounce off each other, okay, lead to nothing. But with the catalyst, all of a sudden a collision that would not have been effective will lead to the formation of the activated complex. And because you now get the activated complex, okay, after that it's kind of all downhill and the reaction will proceed. The key thing is forming that thing. Now the last thing we need to talk about here, honestly, is to talk about the nature of the reactant. And this kind of gets lost here, okay? Let's talk about this. First of all, this is only when we are comparing, right, different types of substances or different reactions, all right? The first four variables are all like saying, well, what would happen in this reaction if we were to increase the concentration of hydrochloric acid? Or what would happen in this reaction if we were to use smaller pieces of zinc versus big pieces of zinc, right? So it's all about the exact same chemical reaction. We recognize that some reactions, just by the nature of what the reactant are faster. So, for example, the alkali metals, right, tend to react rapidly. Alkali metals and alkaline earth. So sodium reacts with water, okay, and so does calcium. This one's faster because sodium is a more active metal. Period. That's just the nature of the reactant. Really important fun fact. In a general rule, when we deal with molecular substances versus ions in solution, these guys will always be faster. Because if they're already ions in solution, there's no bonds to break. All right? Oh, last little really important caveat. I'm actually going to go back to the previous page. Temperature. This is the one area where my students always get things wrong, okay? Because when we get into equilibrium shifts, we always talk about how an increase in temperature favors the endothermic reaction. So and unfortunately, since I'm not teaching this, since I'm not there, it can get really kind of confusing. An increase in temperature does favor the endothermic reaction, but it will always increase the rate of both the forward and the reverse reaction, regardless of which way is endothermic and which way is exothermic. The reality is it increases the rate of the endothermic reaction more than the exothermic one. That doesn't mean it doesn't go faster. So no matter what it says, if they say anything about increasing temperature, both the forward and reverse rate go faster. If they lower the temperature, both go slower. The difference is they don't change the rates equally, but they do change the rates of both of them. That's it. That's collision theory.